NASA launched the James Webb Space Telescope, the largest and most expensive instrument ever flown. The greatest scientific mission of modern times took a giant leap forward on December 25th, 2021, with the launch at lunchtime of the James Webb Space Telescope. When the James Webb Space Telescope turned its gaze toward the mysterious object known as Oumuamua, the astronomical community braced for a historic moment. This was not an ordinary celestial body. Detected in October 2017 by astronomers using the Pan-STARRS 1 telescope in Hawaii, Oumuamua had baffled scientists from the outset. It was the first known interstellar object to pass through our solar system, its trajectory and velocity confirming it came from outside the bounds of our own cosmic neighborhood. For years, speculation about its origin and nature ran rampant. Some saw it as a rogue comet or asteroid expelled from a distant star system. Others proposed more exotic theories suggesting artificial origins. But all of that speculation was built upon indirect data, visual tracking, light curves, and infrared readings. No one had yet captured a definitive image of this enigmatic object until now. Please enjoy the content and share your thoughts in the comments below. The James Webb Space Telescope, with its unparalleled sensitivity and resolution, has finally given humanity its first real image of Oumuamua. Positioned a million miles from Earth, floating in the cold stability of the second Lagrange point, the telescope opened a new chapter in our exploration of the cosmos. Its infrared capabilities allowed it to penetrate the veil of distance and time, capturing details of Oumuamua that were previously inaccessible. The image is unlike any other we have seen. It's not just a blurry blot of light across a grainy background. It's a detailed, high-resolution capture of an object that defies easy classification. What the James Webb revealed was startling. Oumuamua is elongated, yes, but not in the way many visualizations had previously depicted it. Instead of being a cigar-shaped rock tumbling end over end, the object appears to have a complex, almost prismatic geometry. Its surface is faceted, not smooth, resembling the fractured planes of a crystal or the angular hull of something engineered. The coloration revealed by Webb's infrared and near-infrared sensors adds to the mystery. Parts of the object reflect light in a manner consistent with metallic or icy compounds, while other regions appear carbon-rich, absorbing much of the incident radiation. There's a glimmer of iridescence in places, not unlike thin oil on water. It doesn't behave like a comet, nor does it entirely resemble any asteroid known to science. It is utterly unique. One of the most astonishing revelations came from the spectral data embedded within the image. Scientists were able to analyze the chemical composition of the object's surface with unprecedented precision. What they found was a cocktail of compounds that shouldn't coexist naturally, at least not in the concentrations observed. Traces of solid hydrogen, for instance, suggested that parts of the object could have formed in environments far colder than most known planetary systems. There were also hints of exotic ices, some containing oxygen and nitrogen compounds in configurations not previously cataloged. This raises compelling questions about the object's origin. Was it born near a rogue planet, a brown dwarf, or in the icy mantle of a protoplanetary disk circling a failed star? The image also gave insight into the motion and behavior of Oumuamua. Unlike previous assumptions that it was tumbling chaotically, the data now suggests a more stable rotation. The object appears to be slowly spinning along a principal axis, completing a full revolution every 8.3 hours. This adds yet another twist to the story, because such motion implies that internal cohesion is greater than what would be expected from a loose agglomeration of rock and ice. This, in turn, suggests a monolithic structure, or one that is held together by more than just gravity, possibly chemical bonds, or even metallic strength. The precision of the image enabled scientists to model the object's thermal inertia, how it absorbs and releases heat, which yielded another surprise. Oumuamua heats up and cools down far more slowly than expected for an object of its size and composition. This behavior might be attributed to an internal structure that insulates it, perhaps a porous matrix that traps heat, or even a hollow core. Both scenarios challenge traditional models. A porous body wouldn't survive interstellar travel easily. It would be eroded by cosmic radiation and collisions with micrometeoroids. A hollow core, on the other hand, hints at the possibility of artificial design, though that remains in the realm of speculation. What's less speculative is the impact of this image on our understanding of interstellar travel. Oumuamua is not just an interloper. It's a time capsule. It carries within it the chemistry, physics, and history of its origin system. The real image captured by the James Webb Space Telescope offers a glimpse into the diversity of planetary formation across the galaxy. Its very existence confirms that planetesimals, building blocks of planets, can be ejected from one star system and travel unimpeded for millions or even billions of years before briefly visiting another. This makes the Milky Way not just a collection of isolated solar systems, but a dynamic, interconnected network exchanging material across unimaginable distances. The implications for planetary science are profound. Before Oumuamua, models of planet formation considered systems to be largely closed. Now the open exchange of material between systems has to be accounted for. If one such object has entered our solar system, it stands to reason that many more have passed through unnoticed. The Webb image proves that we now have the capability to not only detect these visitors, but to analyze them in extraordinary detail. Future encounters can be anticipated, studied, and perhaps even intercepted. There's also the tantalizing question of panspermia, the theory that life, or its building blocks, can be distributed across the cosmos by celestial bodies. Oumuamua may not carry life, but the complex molecules on its surface suggest it could transport organic compounds. If such an object were to crash into a primordial Earth or Mars or Europa, it might have deposited materials that contributed to the origin of life. With the Webb image, scientists can now analyze whether any such molecules have survived interstellar transit, and whether their structure has been altered by cosmic rays, thermal stress, or vacuum exposure. In the broader context of astronomical discovery, this image signals a transition. We are no longer confined to studying objects within our solar system or distant stars as mere points of light. We can now investigate the physicality of interstellar matter, its shape, motion, and composition through direct observation. The James Webb Space Telescope has become not just a lens, but a bridge connecting us to distant worlds and the silent travelers between them. No less significant is what the image doesn't show. Despite its clarity, the object lacks outgassing vents or visible tail structures typical of comets. It has no clear source of propulsion, no emissions indicative of a power source, and no obvious signs of biological activity. And yet, its geometry and resilience defy simple explanation. This leaves the scientific community with an enigma. Natural or not, Oumuamua does not behave like anything we've cataloged before. The image also poses questions about how we classify space objects. Existing categories, asteroid, comet, dwarf planet, do not apply cleanly to Oumuamua. It might belong to an entirely new class of interstellar phenomena. The Webb image thus challenges taxonomies that have stood for decades, demanding a revision of how we think about the architecture of space and the objects within it. Equally compelling is the cultural and philosophical impact. For millennia, humanity has looked up at the stars and wondered if we are alone. Oumuamua, in its silence and mystery, reminds us that the universe is full of surprises, many of them possibly beyond our current understanding. The image captured by the James Webb Space Telescope is a portrait not just of an object, but of our place in the cosmos. It shows that the universe is not static, but dynamic, filled with wanderers that cross the interstellar void, carrying secrets from other stars. Astronomy at its core is a dialogue between light and time. The light captured from Oumuamua has traveled millions of years, touched countless particles, and passed through vast emptiness to reach our instruments. The James Webb Space Telescope, with its mirrors polished to atomic precision, has now translated that light into information. It has given us a glimpse into the unknown and invited us to question everything we thought we understood. This moment marks a shift in capability and in ambition. For decades, telescopes on Earth and in orbit have expanded our view. But the James Webb has sharpened it. It's not just about seeing more. It's about seeing differently. Through its eyes, we are not just observers, but participants in a galactic story, one that includes visitors like Oumuamua and perhaps countless others yet to be discovered. There is a quiet reverence in knowing that a piece of another star system passed through ours and that we had the tools to witness it in detail. The image doesn't give all the answers. In fact, it raises more questions than it resolves. But that is the essence of discovery. In the end, the image is not just a snapshot. It's a beginning of new science, new theory, and perhaps one day, new contact with the broader tapestry of the universe. Oumuamua is now beyond the reach of most telescopes, fading into the blackness of space. But the image remains, a record of an encounter that hints at the infinite and unknown. As scientists continue to analyze the data, create models, and debate theories, the rest of us are left with the wonder of it all. The James Webb Space Telescope has given us more than just a look at an interstellar visitor. It has given us a reason to look farther, think deeper, and dream bigger. As the world absorbed the astonishing image of Oumuamua, delivered by the James Webb Space Telescope, a quiet but profound shift began to ripple across scientific communities. For the first time in human history, a telescope captured the unmistakable features of an object that indisputably originated from another star system, and did so in such exquisite detail that a new chapter in interstellar studies had to be written from scratch. It was more than just a photo. It was a portal into alien processes, sculpted in deep time and hurled across galactic distances. Researchers immediately began re-evaluating what interstellar objects could be, no longer constrained by the blurry approximations of Earthbound observations or low-resolution tracking from older instruments. The clarity of Webb's image shattered assumptions not only about shape or material, but about how such objects could survive ejection, endure millennia adrift in space, and remain intact upon arrival into another solar system. This new visual record encouraged scientists to model entirely novel ejection scenarios, ones where objects are formed under extreme tidal forces near the edges of accretion disks, flung into the void by chaotic orbital interactions with super-Jovian exoplanets, or born as fragments of massive collisions that tore planets apart. The fine resolution allowed researchers to measure light reflectance from distinct surface zones, each with unique spectral signatures. Some parts appeared coated in highly reflective, possibly metallic compounds that responded to infrared light in peculiar ways. Other areas absorbed nearly all incident light, displaying a signature akin to tholins, complex organic molecules formed through prolonged radiation exposure. These mixed zones weren't smeared together as if blended by impact or erosion. They were sharply delineated, suggesting the object had undergone a form of surface differentiation. That's a feature associated with much larger planetary bodies, not something just a few hundred meters long. This level of differentiation raises the possibility that Oumuamua could be a fragment of a more complex parent body, one that had enough mass and heat to separate elements by density or composition. If so, it would mean we were observing not just a rogue rock, but a shard of an ancient, possibly destroyed world. The idea that Oumuamua could be a geological time capsule bearing witness to a planetary system that has long since ceased to exist added a deep layer of intrigue. The object was no longer a visitor. It was a relic. In light of this, exoplanetary scientists began scrutinizing the structure's irregular surfaces. The object bore the hallmarks of prolonged exposure to both radiation and impacts. Micrometeoroid pits, deep grooves, and a thin veneer of exotic ice all pointed to a storied journey. Yet one of the more curious features was the apparent lack of dust accumulation. Space is not entirely empty. Over millions of years, an object drifting between stars should accrue interstellar dust. The Webb image, however, showed a surprisingly clean exterior, which suggests a form of natural cleansing, either through sublimation, spin-related shedding, or, more controversially, an active process from the object itself. Some physicists propose that Oumuamua might possess a subsurface layer of volatile materials that, when exposed to solar radiation, generated enough localized gas pressure to push away fine particles. Others speculated about piezoelectric effects resulting from mechanical stress during its long voyage, potentially creating electromagnetic fields strong enough to influence its immediate environment. Such phenomena had never before been considered for small interstellar objects and could alter how we understand interstellar physics at the micro level. The rotation rate, observed more precisely thanks to the Webb image, further added to the strangeness. Unlike chaotic tumbling seen in many irregular objects, Oumuamua's rotation suggested internal cohesion, or even a deliberate balance, again opening the door cautiously to theories of intelligent origin. While mainstream astrophysicists remained firmly grounded in natural explanations, a minority of theorists revisited older ideas of alien probes, light sails, or derelict technology. The image didn't prove any of these, but it made such ideas more difficult to dismiss outright. The sharp angular symmetry in some facets, the highly reflective materials, and the clean separation of surface zones, these weren't the usual hallmarks of randomness. Moreover, the image provided data on heat gradients across the object. Advanced modeling showed that the heat was not distributed uniformly, even after accounting for rotation and solar exposure. Some regions stayed warmer far longer than expected. This suggested either an insulating material or, more astonishingly, a heat-retaining core. Such thermal behavior isn't entirely unprecedented. Some comets demonstrate similar phenomena, but not in objects of this size and origin. The possibility of a core or layered internal structure brought new discussions about how interstellar fragments cool over time, how internal gases migrate, and how radiation reshapes the internal chemistry. The implications extended far beyond astronomy. Astrobiologists were particularly fascinated by what such a body could mean for the transport of organics. With its differentiated layers, exposure to cosmic rays, and complex surface chemistry, Oumuamua offered a new model for how life's precursors might be fed across the galaxy. Unlike simple icy comets or chondritic asteroids, it seemed more like a vessel, something capable of shielding, preserving, or even catalyzing reactions over interstellar timescales. Some labs began simulating Oumuamua-like conditions in vacuum chambers, bombarding synthetic materials with radiation while rotating them slowly in cryogenic environments. These experiments aim to test whether amino acids or nucleobase analogs could survive such a journey, and, if so, whether they might arrive intact on habitable planets. The idea of lithopanspermia gained renewed vigor, not as myth, but as mechanism. Oumuamua, as revealed by Webb, offered the clearest case yet for such a process not only being plausible, but possibly common. The image also led to speculation about what other interstellar objects might look like. If Oumuamua was this complex, what might the next visitor bring? Would it carry isotopes never seen before? Would it spin in impossible patterns or respond to solar radiation in bizarre ways? The Webb image prompted astronomers to re-examine archival data for overlooked interstellar candidates. It also catalyzed the design of new monitoring systems to catch such objects earlier, perhaps even early enough to launch missions to intercept or rendezvous with them. Space agencies began drawing up mission concepts to prepare for the next interstellar visitor. The ability to image one object so precisely had stirred ambitions to go further. Proposals emerged for high-speed probes equipped with high-resolution cameras and mass spectrometers, powered by solar sails or compact nuclear reactors. These craft, launched in anticipation of a newly detected object, could fly alongside a future Oumuamua analog, sending back real-time data on composition, structure, and maybe even origin. In parallel, theorists proposed using Webb to conduct a deep survey of space along the direction from which Oumuamua came. If one object had been ejected from a system, perhaps others had followed. A family of rogue bodies might be drifting through the void, remnants of planetary collisions, failed stars, or ancient debris fields. Webb sensors could potentially detect subtle variations in background infrared light that hint at the presence of such fragments. As the implications multiplied, so did the philosophical considerations. The realization that an object older than recorded human civilization, perhaps older than life on Earth itself, had passed within a cosmic stone's throw from our planet, brought a renewed sense of humility. Here was a shard of a distant place, a silent messenger from a past, and a people we might never know. It carried no signal, made no attempt to communicate, and yet, in its silence, it said more than volumes of science fiction ever had. There was something haunting in the symmetry, something graceful in the trajectory. The Webb image, frozen in time, depicted not a ruin, but a survivor, a hardened relic of starfire and gravity, sculpted by cosmic weather, shaped by forces humans are only beginning to understand. It didn't need to be artificial to be awe-inspiring. Nature, after all, is the oldest engineer. Some scholars in the humanities began exploring the cultural significance of this event. Artists, poets, and philosophers examined how the image reoriented our relationship with the universe. This wasn't a telescope seeing deeper into our own backyard. This was a keyhole view into someone else's. The colors, the angles, the shadows, these became symbols in galleries and metaphors in literature. In a way, the Webb image bridged science and storytelling, offering a new lens through which to contemplate origin, destiny, and the cosmic unknown. Meanwhile, educators used the moment to ignite passion in the next generation. Images of Oumuamua made their way into classrooms and public lectures, becoming a visual anchor for discussions on interstellar distances, orbital mechanics, and the nature of scientific discovery. No longer did teachers have to rely solely on simulations or artist renderings. They had a real image, a beacon from beyond. It's worth noting that all of this emerged from a moment of timing and fortune. Oumuamua entered our solar system just when humanity was beginning to develop the tools to notice such fleeting phenomena. And Webb, positioned perfectly and operating at the right wavelength range, was able to capture it before it disappeared into the abyss. That convergence of technology, curiosity, and cosmic happenstance will be remembered as one of the great milestones in our journey to understand the universe. Though Oumuamua has now faded beyond the reach of direct observation, its legacy has only grown. The image remains a benchmark for what's possible and a template for what's to come. It redefines the boundaries of observation and demands a recalibration of our assumptions about the galaxy. In time, this single object may inspire an entire branch of astronomy, the systematic study of interstellar visitors. With advancements in telescope technology, space-based sensors, and high-speed propulsion, it's likely that Oumuamua won't remain the only object of its kind to be analyzed in such detail. But it will always be the first to show its face, the first to be caught in full color, the first to whisper across light years and be heard. The data from the Webb image continues to yield new insights. As more sophisticated algorithms extract deeper levels of information from the captured spectra, the object's composition becomes ever clearer, its motion more precisely plotted, and its history more richly inferred. Scientists are finding new ways to simulate how interstellar radiation affected its outer layers, how micrometeorite impacts shaped its form, and how gravitational forces from distant stars might have nudged it onto its epic voyage. It's likely that for years to come, this one image will serve as a foundational reference across disciplines. In planetary science, it will redefine ejection mechanics. In astrobiology, it will influence models of molecular migration. In astrophysics, it will challenge conceptions of non-Keplerian motion and radiation dynamics. Even in the nascent field of interstellar archaeology, the study of non-terrestrial artifacts, it may one day be viewed as the first specimen. And yet, even amid the immense scientific impact, the image carries something subtler, a quiet astonishment, a recognition that the universe is more vast, more complex, and more interwoven than even the boldest theories suggest. Oumuamua's passage is over. Its moment in our sky, past. But through Webb's lens, it lives on, not just as a photograph, but as a revelation. As scientists delved further into the data supplied by the James Webb Space Telescope's capture of Oumuamua, a cascade of new hypotheses emerged, each more intricate than the last. This was not merely a moment of confirmation, it was a provocation. The clarity of the image brought with it a level of complexity no model had prepared for. Tiny shadowed indentations, ridges running parallel across certain planes, and sudden geometric discontinuities told a story written in form rather than function. Even the orientation of its angular structures suggested interactions with unknown forces during its voyage, subtle influences that left permanent marks. Perhaps most unexpectedly, attention turned to how light interacted with the object in motion. As Oumuamua rotated, its surfaces didn't simply reflect infrared radiation, they refracted it in peculiar anisotropic patterns. This behavior was entirely alien to known natural bodies of its size. It hinted at crystalline structures embedded within, or perhaps coating the surface with orientations aligned in ways suggestive of growth under extreme pressure, or perhaps artificial ordering. Laboratory attempts to recreate similar reflection patterns fell short, unable to mimic the sharp transitions and bandwidth of reflected wavelengths seen in Webb's data. This further opened the field to consider materials we have yet to encounter in nature or those formed in environments beyond Earth's understanding. Regions near neutron stars, around magnetic white dwarfs, or in the interstellar medium under intense galactic cosmic rays. Looking beyond structural analysis, the Webb image also opened up an entirely new realm. Surface topography as a chronicle of time. The object's skin, as revealed in minute contour, seemed like a stratified document, recording impacts, radiative degradation, and perhaps erosion from gas-rich environments. Advanced photometric modeling revealed subtle depressions on one face consistent with sustained exposure to particle winds, suggesting a past passage near a highly active stellar corona. If true, this meant that Oumuamua's voyage brought it not just through cold vacuum, but through regions of high energy that left visible scars on its body. These regions could be mapped, cross-referenced with simulations